Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to take all of our knowledge of rotational motion and try and apply it more specifically to rotational spectroscopy. So get ready for some wave numbers. So far what we've established is that we can determine the energy of a three-dimensional rotor by solving essentially the energy in each of the individual axes by knowing the relevant moment of inertia and the angular velocity. This can be translated into the angular momentum in each of the three directions, again, corrected for the relevant moment of inertia. Now, for spherical systems, this is actually quite a simple sort of equation to use, because it turns out that when all of our moments of inertia are identical, that term essentially becomes shared. And then all we're left with is the energy being dependent upon the sum of our individual component angular momenta divided by twice the total moment of inertia. Now here we also get very lucky in that our sum of the individual component angular momentums is just our total angular momentum, because who doesn't love a nice simple expression? And as a reminder, we can find our total angular momenta based on our angular quantum number. So here I want to make note of a difference in symbols. So previously, when we were dealing with a more general angular momentum, we gave the angular momentum quantum number a value of L. However, your book at this point tends to use J, and even worse, they use an uppercase J to represent molecular angular momentum. So for this, I do apologize. And if you may have noticed, I'm trying to denote the value for the angular momenta as a bolded J and the quantum number as the unbolded J. I do sincerely apologize that the book decided to use the same variable for these two things. So keep an eye out, and when in doubt, try and use context to help figure out whether we're talking about the value or the quantum number. If nothing else, this one has no units. The value will. So that's one of the tools you can use to try and help yourself out. But again, I do apologize for this. But we can actually determine our total angular momenta based on our quantum numbers. And we can then plug this back in for our energy value. So this case, we actually get fairly lucky, as we've actually pre-solved most of this when dealing with a simple diatomic rotor. None of the equations really change because we're still only dealing with one single moment of inertia. However, one of the things I do want to make note of is the biggest difference is that the angular momentum can actually be pointed in a variety of directions, because no longer do I have movement just in a, say, XY plane, while that plane may be rotating. Now I have a more kind of complicated motion or rotation when I go to a full spherical system. This has no implication on the energy levels. The only implication it has is on the degeneracy. So essentially, the result is I take my normal degeneracy numbers we had for the diatomic system, and they now become squared. So, yep, every axis you add, you pretty much square the degeneracy. So yeah, this does get a little bit out of hand. But other than a difference in degeneracy, no major differences in between spherical and diatomic. Now, just as a reminder, we will still have an angular momentum in the z direction, and this will still be given by our good old equation for the diatomic system, h bar times the what's now called the magnetic quantum number. So again, one of the reasons why is this directionality of the angular momentum often results in some magnetic moments. But again, this will still have values going from negative j to positive j along integer values. So again, nothing too different here for a spherical rotor. Linear rotor, again, this is mostly going to behave just like our diatomic system, so it won't really matter whether I'm diatomic or triatomic. Again, just watch out if we have 3 or more atoms, because then we can start playing a little havoc with that moment of inertia. But one of the biggest differences is that now it only has 2 different moments of inertia, because the other one goes to 0. And as a result, the only big difference is we drop the degeneracy down to simply 2j plus 1. So reduced degeneracy for the more constrained rotation. Otherwise, most of the energy levels behave just the same. And again, we still have the same behavior of angular momentum in the z direction, still given by our angular momentum quantum number. However, one of the things we want to try and do is, just like we did with vibrational spectroscopy, we want to try and move this from our classic physics energy description to, since it's spectroscopy, time to get ready for some wave numbers. So the first thing we're going to do is replace our constants out front with a rotational constant, beta. So this is going to replace our h squared over 2i. However, we are going to try and leave an hc out front. This way we have a unit conversion from wave numbers to energy. That's really all hc is doing here. And the this beta rotation b rotational constant is simply going to end up as a ratio of our Planck's constant, a 4 pi correction, speed of light ends up having to be in here to cancel out the conversion later, and a moment of inertia. So again, nothing too complex, but again, watch out for those moments of inertia when you're dealing with your system, and make sure you've calculated those correctly. This will be the major difference in between a diatomic, a triatomic, and a spherical rotor. So again, watch out for that. And again, just like we saw with the diatomic system, we tend to find our energy levels being very closely packed down at the bottom, and then increasingly separated as we go up. So again, we'll tend to find most of the occupation at these intermediate levels, where we balance degeneracy with energy separation. However, one of the things that we can do is, using this description of the energy in terms of the rotational constant, we can also then express the energy sheerly in terms of wave numbers. So this will mostly occur just by getting rid of that HC unit conversion, leaving our system explicitly in wave numbers. So this actually yields us a fair, this is where the rotational constant really starts to shine, as we can simply get the energy level in terms of wave numbers simply as the rotational constant times our rotational quantum numbers. However, because this is spectroscopy, I care a little bit less about the energy of any given state, and I care much more about the energy separations. We can get at these energy separations simply by taking the difference of a ground state in state J and the state directly above it of J plus 1. We can then take our expression in terms of the energy in terms of wave numbers, so input that in for both of these terms. Now, one of the things you'll note is on this first term, J now becomes J plus 1, J plus 1 now becomes J plus 2. And then we subtract out, again, our basic energy term. Now, in order to simplify this equation, it is worth noting you are going to need to do some distribution of this first term. And when you do that, you will notice there will be some cancellation of terms. And actually, it turns out the resultant energy separation is kind of elegant. It's simply going to be twice the rotational constant times the the initial quantum state plus 1. And again, it makes sense it's the quantum state plus 1 because if I start in the ground state with no rotational motion, I do indeed need to have an energy separation here of twice the rotational constant. And then it goes up to 4 times, and then 6 and 8 and so forth. Each separation essentially increasing by twice the rotational constant, till by the point that you get up to, say, going from the 15 to 16, it's now it's now 32 times the rotational constant. So this is going to be a nice, elegant way of trying to get at our rotational spectra. However, one of the things I do want to make note is that when we're dealing with rotational spectra, we almost always have multiple states being occupied. So whereas a vibrational spectra tends to have one nice, elegant spectroscopic signal, the same thing isn't going to be true when dealing with rotational spectra, because it turns out that I'm going to have all of these signals, all with their own characteristic wave numbers, which means, yes, they're all absorbing different wavelengths of light, all occurring simultaneously. However, you can, to a certain extent, get at the abundance of the system in any given rotational level simply by the peak height. The higher the peak, the more states were originally, the more molecules were originally in that initial state. This is also complicated, actually, in truth, probably simplified by selection rules. So just like with a vibrational state, we were only allowed to increase its vibrational quantum number by 1. It turns out that there is a strict rule that only allows angular quantum numbers to change by 1. So increase or decrease when absorbing or emitting a photon. So as a result, if I'm doing, say, microwave spectroscopy, I absorb a photon to excite the rotational levels. My J should increase by 1, and any emission should be related to a decrease by 1. So again, our selection rule, our rotational quantum number should be plus or minus 1. However, the change of m sub j is a little bit tricky because, of course, it can also increase or decrease by 1. But it's also possible that any increase in the angular momentum, instead of going into the z direction, instead went into the x or y. So it is actually possible for m sub j to stay constant, even upon an absorption or a photon emission. However, one of the things that is worth noting is you can actually couple rotational spectroscopy to electronic excitations or vibrational excitations. And when this happens, it's going to be possible for, say, a photon absorption to actually cause a decrease in the angular quantum number. And we'll talk about this much more in detail in 2 lectures. However, next lecture, we're going to go away from the simple systems of linear and spherical molecules and deal with that mess that is the symmetrical rotor. Until then, take care.